Yes, good morning. Good morning, everybody. I mean, it's morning in Montreal. Welcome to our AI R&D Center. So this center has been created in 2020 by SKEMA Business School with two missions. I mean, like the first, of course, is to conduct research, and then research applied to AI research applied to business. And this masterclass will reflect the research of one of our professors here. But the second axis is a development of application for business, of AI application for business and machine learning. And, we have as a responsibility to develop courses for all our campuses around the world, and also to prepare executive courses in data science and machine learning for the local community. We also develop applications specialized in finance, marketing, and supply chain. And all of this is done by a team of researchers and developers who are in Montreal. And we have today's pleasure to welcome Leopoldo Bertossi, one of our professors, who will talk about explainable artificial intelligence and classification system. Thank you, Leopoldo.
Well, hello everyone. Good morning, good afternoon, depending on where you are in this moment in the world. It's a pleasure to be here. I mean, presenting some of the recent research I have been doing in artificial intelligence and explainable AI in particular. I have to thank Margarita for having made this presentation possible, the Masterclass, and also to René, Madeleine, Catherine, and the whole team that we have here. So thanks a lot for being here today. So the purpose of this presentation is threefold. One is to show a bit of my recent research, a bit of what we do here in Montreal, and also to invite people to collaborate, because I'm going to point to some research direction. So collaboration is welcome, and if you are interested, I mean, please contact me. Here you have my email address, and I would be happy to talk offline at some point with all of you. Okay, so I'm going to talk mainly about explanations in artificial intelligence, touching upon the application to classification systems. So let's consider this situation where we have an entity that is represented as a record of feature values. This is a person who has a name, has an age, has an occupation, has a salary, a place, a neighborhood where he or she lives. So it is a record with feature values for different features, in this case, name, age, activity, income, etc. Yeah? And then this entity requests a loan from a bank, which uses a classifier to make a decision. Yeah? So this is the bank. We have entity here asking for a loan, and the classifier actually responds no. The loan is not granted, is not accepted. That would be the label of the classification system provided for this particular input. Yeah? So the client asks why I'm not given the loan. Right? Well, when we start talking about why, of course we are talking about explanations. So what kind of explanations should we give to this person, right? Or the person who is in charge of the system, who also wants to know why this decision was made. Yeah? So how did we come to this decision? From what? On what basis? I mean, so there's different things that have to be clarified here, right? So this problem is representative of a more general situation in applications of AI systems in these days. It's a very important area of research. Users and those affected by the results of AI systems, the stakeholders, they request explanations. Yeah? That is the idea. And actually a whole area of artificial intelligence has emerged that is explainable AI. I will I want to start by making a case that this is part of artificial intelligence, because I have heard some people saying that this is not part of AI, it is something like at a higher meta level. I don't think that this is the case. Actually, for several reasons. AI systems should be extended with capabilities to provide explanations as a part of the system, I think, and that becomes part of the artificial intelligence research and practice. Yeah? And actually, AI researchers and professionals, I mean, are those who understand these systems, so they should be involved, and these are usually AI people, right? In the same way as mathematical logicians, at some point, they started studying the methods and the scope of mathematics as a whole, and this was carried out with the methods of mathematics and by mathematicians, not by someone at a higher level who didn't understand the details of the mathematics involved. Right? So, and also because human beings, they give explanations, right, as a part of their intelligent activities, right? So, in this case, explanation building should be a capability of artificial intelligence agents as well, so as human beings are able to provide explanations. Yeah? So then explanations have to be understood, they have to be modeled, they have to be implemented, and all this becomes part of artificial intelligence. Yeah? So we are doing here artificial intelligence. Yeah? Explainable artificial intelligence is of interest to many other people, not only to the research, of course. We talk about stakeholders being affected by the outcomes from AI systems. The person who applies for the loan is affected by the system. So these outcomes could come in the form of assessment, for example, a credit score, or classification, good or bad client, or decision, approve or reject the loan, etc. So those are the outcomes that may affect different stakeholders. Yeah? So a whole discipline has emerged in the last few years that is more broader than just explanation, that has to do with ethical AI. Yeah? Yeah. And this area, of course, touches many others, I mean, including artificial intelligence itself, but it goes much beyond that. I mean, law, sociology, philosophy, and business in particular, that is part of our business. Yeah? So this area emerges naturally and motivated by the need for more transparent, trustable, fair, unbiased, etc. You can use many qualifications of AI systems. So this is a whole package of considerations that are brought into the umbrella of explainable AI and ethical AI in more general terms. We also want to be able to interpret AI systems, to understand them, what is going on with them. I mean, so that is also very important. So it is commonly the case that we have an entity applying for a loan, and the classifier, I mean, the answers no. But what is this classifier? Actually, on purpose, I depicted it here as a black box. So sometimes people do not even understand what is going on inside. I mean, it's really a black box. Yeah? It can be a very complicated model, so interpreting the model is a challenge, it's a task. Yeah? So it may really be a black box, as I indicated here. So what can we say about the classifier? And actually, it's also important to take into consideration that there are new legislation in place in several places and countries in the world that is forces the AI system and the owners of AI systems that affect users to provide explanations and guarantee all the above. I mean, transparency, trustability, fairness, unbiasedness, etc. Yeah? So this is the overall picture, and so what we are doing falls under this more general umbrella. Okay, let me talk a bit about explanations in AI, and talk about explanations a bit in more general terms than only AI. The important thing is that the search for explanations belongs to the nature of human beings, yeah? And it has been around much before the inception of artificial intelligence, of course. So this quest is a long one that started, as I said, I think, with the early human beings. Yeah? They wanted to explain why things happen. Yeah? Actually, the ancient Greeks, I mean, already were concerned with the notion of causes and, of course, of effects. we find already in Aristotle, some reflections around this problem of characterizing causes and effects. The explanations have been studied also by philosophers, logicians, physicists. In physics, cause and effect is all the time a very important problem. So the question is, are explanations a new subject in AI? Well, at the light of what I just said, basically I would say yes and no. And yes, because, at the light of AI system, the whole idea of explanations takes new forms, right? And is shaped according to different needs. So explanations have been studied in AI for some decades by now, and in related disciplines like logic that has a long tradition. Modern logic started with Boole and then continued with Frege by the end of the 19th century. So it has been around for a long time, much longer than AI. Actually, logic is the basis of AI, is at the very root of AI, but I'm not going to go into that. And a statistic, of course. Statisticians also want to provide explanations of different kinds, particular causal explanations. Yeah? So some forms of explanations are new in AI. So that's why I'm saying yes and no. There are things that are older, things that are new. So some other explanations in AI have roots in already existing ones. And I want to provide in the first part of this presentation some ideas of what has been done in AI around explanations. People tend to reinvent the wheel, but there are many things that already exist, and we could take advantage of them. Right? That is my main message. Okay, so I'm going to talk about model-based diagnosis that has been a part of AI for decades by now. It has been an area of AI for some time, much before the new fashion, so to say, of explaining AI. It's about doing a diagnosis of a system that is exhibiting some sort of unexpected behavior using a model of the system. It is called model-based diagnosis. We need a model of the system, and possibly a bit more than that. So let me try to illustrate. I think I'm going to be using this example throughout my presentation. It's a very simple Boolean circuit, but could be a classifier. What do we have here? We have here a circuit. We have input gates. This doesn't show here. So we have A, B, and C. They are inputs. They are binary inputs. They just say true or false or one or zeros. Yeah? The A and B, the inputs go into an AND gate. That is A, 1. I'm suggesting that this could be much larger than this very simple circuit. But I already need this. This circuit is good enough to convey many of the ideas I wanted to present. Yeah, so there is an output X from this AND gate, and that goes into an OR gate. That is the second one over here. And then this OR gate has another input that is C, 1 or 0. And what we get in the end, if we evaluate the circuit, is D. Yeah, is also a binary variable, take the value 1 or 0 or true or false. Yeah? Okay. As I said, this could be a classifier in the sense that we could have an entity encoded as a string of zeros and ones, the feature values for the features, and then at the end we get D as a label, yes or no. We give the loan or we don't give. Of course, it is not going to work as a classification system for such a, let's say, a financial application, but I hope it conveys the gist. Yeah? So in this case, we use these inputs, 1 for A, 0 for B, 1 for Z. Yeah? If the circuit behaves according to what we expect, we should get actually what we get. If A is 1 and B is 0, X should be 0 because A, 1 is an AND gate. So the two of them should have to be 1 in order to get 1. So X is 0. And then with C equal to 1, going into an OR gate, that is good enough to make D equal 1. However, the circuit this is what should happen, right? So, and this is what we are getting. Are we fine with this? I hope it is clear. However, we use the same input, and suddenly the circuit or classifier is producing a 0 as an output, as a label. So what's happening here? That is the so why? What is wrong here? There must be something wrong, because it should be a 1 and we get a 0. Yeah? So we have to provide a diagnosis. Yeah? A diagnosis. And well, the natural question is, what is the diagnosis for this malfunctioning of the system that is returning a 0 instead of the expected 1? So we want a diagnosis, but of course we need a characterization of what the diagnosis is. I mean, we have to model, this notion of a diagnosis. Yeah? So this is the circuit 1 in order not to lose track of what we are doing here. And then we have here a logical model of the ideal circuit as it should behave. So what I have here is basically say X is equivalent to A and B. This is the intermediate output that we had. And then D, the final outcome, should be the OR of X and C. That is what the circuit should represent and compute. Yeah? Okay, so this is a model of the ideal circuit working under normal conditions. And then we have this observation. It basically consists of A is equal to 1, B is equal to 0. That is why I have not B. So A stands for the value is 1. So not B means the value is not 1. That means it has to be 0. C is equal to 1. And what we get here for D is not D, it's 0. Yeah? This is an observation. And we have to somehow put these two things together. Right? And what is happening here is this, I put these two things together. Basically what they have is an inconsistency, because the circuit under ideal circumstances should return a 1, and we are not observing this. Okay? So what can we get for the combination? As I said, logically, hopefully using some sort of logical reasoning. So the combination is inconsistent. Everything, what do we get? Well, we get everything, because when we have a logically inconsistent theory, you can derive anything. You may have seen that in math, in your first courses of math. When you introduce somehow an inconsistency, you end up deriving anything like 1 is equal to 0 or something like that. So in the presence of inconsistency, classical logic basically will allow us to obtain everything. That means nothing relevant, because we get everything. So in this sense, we get, this is trivial, irrelevant, useless conclusion. Yeah, everything can be obtained from this. So we need more. We are not going to go very far with combining these two pieces of knowledge. So we need a flexible model that allows failures, not anymore the ideal circuit, but something that allows failures. Yeah? So this is what we are going to call a weak model of failure, especially things, specifying what things happen when everything is working normally. Yeah? That is a model that is going to be more flexible than the ideal one, admitting possible failures. So this would be a revised model. What I have is basically, what is this saying? In red here, you have, if the A gate is not abnormal, so I have introducing a new variable, not abnormal A, means that A is not working properly, or is abnormal in some sense. So when it is not abnormal, then X is the result of the gate under usual ideal circumstances. When the OR gate is not abnormal, then D behaves as the OR of X or C. But now we are at least admitting the possibility of having some failures, because not everything has to be normal. Yeah? Okay, so this is, I hope this is fine. If there are questions, I'm happy to. So now gates could be abnormal or faulty. Yeah, that is, we are making some progress in this direction, right? Okay. Okay, now if I put together the observation with the model, now this is perfectly consistent, because I am allowing things to be abnormal. There is no inconsistency anymore. Yeah? So I might be able to derive interesting things from here, from this new combination. Of course, if I take the observation, the model, the new model, plus the assumption that everything is behaving normally, that this is the A gate is not abnormal, the O gate is not abnormal, I am back to the situation I had before, and everything turns out to be inconsistent, as before. Yeah? Are we fine? Okay, so something has to be abnormal to restore consistency, so to say. Yeah? And this is the game we are going to play, okay? And now here what I have is the definition of what the diagnosis is. I'm not using the definition and the formal characterization, but the example will show how the definition goes. So D, saying that the OR gate is abnormal, is the diagnosis, and now it is the definition, basically, because if I make the gate O abnormal, I restore the consistency that I had lost by assuming that everything was perfectly fine. Yeah? So now you see the difference. Everything was abnormal. Now I'm making the OR gate abnormal. And now this turns out to be consistent. So I switch from inconsistency to consistency. And that is why the abnormality of the OR gate is a diagnosis for the malfunctioning of the system. Yeah? It's a very precise definition. Not stated as a mathematical definition in formal terms, but this is it. So the abnormality of gate O is an explanation for the malfunctioning of the circuits. That is our reading of this. Now let's consider a new potential diagnosis. I mean, now everything is abnormal. Yeah? Still, it is a diagnosis, because making every gate abnormal restores consistency as well. Now I'm switching this to abnormality, and this one to abnormality. Abnormality as well. So now I have consistency. I could say this is the diagnosis. However, you can see one thing that is important. This diagnosis involves the other, includes the other. So maybe it's not a very good diagnosis. Yeah? So D, the first one, is better than D prime. It has fewer assumptions, is narrower, is more focused, and more informative. So then you can start telling apart good diagnosis from bad diagnosis, or not so informative diagnosis, so to say. This is what is called consistency-based diagnosis. It was introduced by Ray Reiter, prominent AI researchers who unfortunately died too early. And then he presented his paper, a seminal paper, very important one, in 1987. This is consistency-based diagnosis in a nutshell. Okay? And one question that we could think about, I mean, is can we assign scores to diagnosis? And I think I will illuminate this discussion a bit more. For example, the first diagnosis should have a higher score than the second one. Yeah? There is another class, a kind of diagnosis in the AI literature, and actually beyond AI. It has been studied much earlier in logic than in AI. It's also a classic form of model-based diagnosis in AI. So we have the very typical example. We have COVID implies a fever. I know this is not always the case, but this is the very simple model we have. Okay? And then I observe that someone has fever. Yeah? So what can I do with this? Well, this is the only information I have, so I am tempted to make the conclusion that COVID-19 is the cause or the explanation for the fever that we are observing. Yeah? So without further information, we would like to infer that COVID-19 has an explanation. However, notice that this is not logical inference in the classical sense, because we are using the arrow in the wrong direction. Yeah? Usually you have the antecedent of the implication, that you conclude the consequent of the implication. We are using the arrow in the wrong direction, according to classical logic. Yeah? So not classical logic-based deduction. This is not classical logic-based deduction, but abduction of an explanation. I'm trying to abduce an explanation, something that actually supports what I am observing. In this case, a case of fever. Yeah? So if I put together COVID-19 together with a simple model, we imply the observation. But I have to add this as a piece of additional information, and that becomes my explanation in this case. Yeah? It's a very classical example. There are many complicated things underneath. I mean, this model could be much more complicated, as you can imagine, but I think this example shows the gist. So this is sort of backward reasoning in search for explanations that support implications. I mean, we are reasoning backwards somehow in order to find possible explanations that support the implication, and then we verify them by forward reasoning. If I put these two things together, I am really implying classically the observation. Yeah, this is it. So, abductive or sufficient explanations, as they are called as well, are relevant in explainable AI. So people are using them, they are investigating them, and still there are many things to do in that direction. But this has been around much earlier than new, let's say, fashion, as we see it today. Okay? So people are still using this. And actually, there are connections between these two forms of model-based diagnosis, consistency-based diagnosis and abductive diagnosis. I mean, I'm not going to delve into the details of the connections. There is a very interesting thing to see here. Just to come back to the example from the point of view of abductive diagnosis, that's what we are talking about now. Let me try to do something with this example. I can have this model here on the right-hand side. You see that when O is not abnormal and I have the input C, the one here, then I should get D. And then I'm getting not D. That is the point. I'm getting not D. Yeah? And obtaining not D. If I have the abnormality of O is not abnormal, I mean this gate is not abnormal, and I have X going into O, well, I am also getting not D. That's what I am observing, right? And then, well, that is the most important thing. I also have something similar for this variable over here. That is the output for this gate. And also, I have the observation as a part of what I'm seeing and modeling logically. I have the A is 1, B is 0, C is 1, and not D, and D is 0. Yeah? This is what I have. So I try to find out why not D is true. Yeah, it is very similar to the example I showed before, a bit more complex. As I said, this can be arbitrarily complex, but not in this. So we start from D at the very top here, and then we try to find support for what we observe. All right? So start from not D in 1. We reason backwards, try to find what is needed to prove it, according to classical logic. I mean, yeah? So hopefully we are going to reach, through this process, an abductive variable, something that will provide an explanation, will be an explanation. Yeah? So if I combine 1 and D in 2, 1 and D, I have not D, and I have not D and in 2, basically I'm going to have that this has to be true. I mean, the value of the rule, the antecedent of the rule, not abnormal. O and C has to be true. So this is a part of the backward reasoning. Yeah? So now I see I have to somehow establish the normality of O and combine with C. But then I look at the observation and I see that C is true. So I count with this to be 1, and I can basically drop this here, and I'm going to be left only with this. Because if this is 1, this is equivalent to this. Yeah? So, since C is given in 2 explicitly as true, we reach the abnormality of O as is all is needed to obtain not D. And that is the way we obtain an explanation for the observation not D. Yeah? Well, this is an alternative formulation, but I don't know going to go into this. I hope I made the point. So these things have been around for some time. And now let me talk about something that is, well, actual causality. I'm going to talk about causality. Causality has been around also for some time, but how would be a causal approach to this same problem? So we have the same circuit as before, and then this is the model we had. Yeah, I'm not changing anything. I also have my observations as before, combined with the model, and also I'm assuming that everything is normal, so we know from the a couple of slides ago, that this combination has to be inconsistent. Yeah? So, what I'm going to try to do is to play a game. What if I start changing things, right, in order to switch this conclusion that we have something that is inconsistent? Yeah? In this case, when we do actual causality, we usually assume that there are some things that are endogenous variables, basically those are on which we have some control that we can play about with, and the other things are fixed. We are not going to play with the inputs because that's what we have, or the output, that is a given. So we can only play basically with the abnormality or normality of the gates. The rest is a given. They are called exogenous variables on which we don't have much control. Okay, so this expression here, the inconsistency, is logically equivalent to this implication. Why? Because what this is saying here is whenever I make the left-hand side of the implication true, D has to be true. Yeah? So whenever I make here in this part everything that is in blue, everything that is in blue true, I know that D is going to be true. That's why when I have not D, this becomes inconsistent. So this is another way of putting this inconsistency statement in terms of a classical logical implication. The two things are logically equivalent, mathematically equivalent. So I can start playing with implying D or not implying D by making changes, counterfactual changes, as we are going to call them, on the endogenous variables that are the abnormality atoms or pieces of information. Yeah? So counterfactuals, they are basically hypothetical changes on non-abnormalities into abnormalities to see if the implication changes. This is we play a game. If we change things, is something going to change or not? This is the idea. So in this case, if I keep everything the same, but I change here this not abnormality to abnormality, then I do not get D anymore, because we saw before that by making this change, we got a consistent theory that included D, so D, not D, and so D cannot be implied, basically. Yeah? So the idea here is that by making this minor change, this counterfactual change, hypothetical change, we switch from D to not D. Yeah? Or we disallow the implication of D. Yeah? So the implication was switched. And we make one change. And this is good enough to call the abnormality of O as a counterfactual explanation for the observation that we had before. So the abnormality of the OR gate is a counterfactual cause for observing not D. Yeah? Counterfactual cause. Notice that here one change is good enough to switch the implication. Yeah? This is the very simple example. I hope I convey the gist. Of course, if I change, now I'm considering the other potential counterfactual, that making only this one, I'm changing now this one here, yeah, to abnormality. I'm keeping the O, the abnormality, the not abnormality of O as it was. Then nothing changes. I am still implying D. So the abnormality of A is not a counterfactual cause because I didn't switch the implication by making this change. So maybe what I need here is to make additional changes. Yeah? So we make an extra counterfactual change that might be necessary here, and then I'm going to switch not only not ABA into ABA, but also not ABO into ABO. So we have now, so I'm changing this, and this becomes a contingent change for this other change. And then the combination of the two changes does switch the implication. So what do we have here? We have basically that AB, the abnormality of A alone was not enough to provide an explanation, but if I assume additional information, I'm in position to obtain an explanation according to this methodology. But unfortunately in this example, I mean, the abnormality of O is good enough to explain things. So if it wasn't the case that the abnormality of O is a counterfactual cause, then in this case we would have called the abnormality of A would have been an actual cause, an actual cost, with a contingent set, something in addition that has to be changed as well in order to restore consistency. So that would be basically the definition of what is an actual cost. It needs additional changes. Something needs additional changes. So we have the counterfactual explanations or causes that are the strongest ones, and then we have these actual causes that need some company, so to say, to produce a change in the model. Yeah? They are weaker causes in some sense. And actually this can be quantified, right? So the abnormality of A is neither counterfactual nor an actual cause. Yeah? Well, let me say that this actual consistency was introduced in the literature by Joe Halpern and Judah Pearl in 2001. One of the possible approaches to causality. And basically, actual causality provides what is called also in the AI literature in these days, in the explainable AI literature, contrastive explanations that have to do with this counterfactual game. Yeah? As opposed to the sufficient explanation that we had in the case of abduction. So it should be more or less clear, at least intuitively, that there are some correspondences with the other forms of diagnosis. Actually, this is in some sense very similar to consistency-based diagnosis, playing with same kind of changes. Yeah? And it is also possible to establish bridges with abduction. And we have done this before in some particular scenarios. I will say more about this. What about assigning numerical scores to quantify the strength of a cause? I mean, I want to assign a number. Well, this can be done through causal responsibility that was introduced by Chocolate and Halpern in 2004. What is the idea? Very simple here. I'm going to come back to this. The responsibility of the abnormality of the OR gate as a cause is basically 1 over 1. This is all the time. And then I see what is the minimum cardinality of a contingency set that I need in addition to this change, the abnormality of O. In this case, I didn't need any other change. So the cardinality of a contingency set, the minimum one, is the empty set that has cardinality 0. So it is 1 over 1 plus 0 equal to 1. And this is the maximum responsibility a cause can get under this responsibility model. Are we fine? Please. And responsibility of abnormality of A is 0 because it is not an actual cause. Yeah? Because basically the other gate involves this other one or supersede this possible explanation. So you can assign scores to this. Yeah? People may say, well, I have this actual causality scenario, but maybe we are missing what we usually see causal networks, I mean, in the causal literature, in particular in AI. Well, actual causality as presented may not look like causal networks or structural models used in AI. And actually, it's not difficult to produce, to formulate the example in these terms. Basically, what they have here is a network. D is the output variable. The input variables are here A, B, and the possible abnormality of A has to be brought into the picture. They produce a variable X, right? They have effects on variable X over here. Yeah? And then this X becomes one input variable to the lower part of the tree, the graph here is that also takes C as an input and the abnormality of O as a possible input, and we get D. And what we have on the right-hand side are basically what we call structural equations, yeah? In the sense that they explain the connection between the variables over here and the output variable. So basically what this is saying is that X, when A is not abnormal, behaves as an AND gate, the usual AND gate. And the other possibility, when it is abnormal, it actually behaves as a NOT, the negation of the OR gate. So basically, this fully describes X in terms of the inputs here. And here, the same here, when when O, the OR gate, is not abnormal, this one here, then D behaves as the OR of C and X. And when it is abnormal, basically we get the negation of the AND gate, that is of the OR gate. Sorry. Yeah? So basically it's a very simple a structural model with a causal network. So here, as I said before, ABA and ABO are endogenous variables. Usually in these causal diagrams, we identify the endogenous and exogenous variables. So those are the variables that can be subject to counterfactual changes. The other are called exogenous variables. So in this case, only those in red are the counterfactual, the endogenous variables. And the links have a structural equation. So this is, everything can be cast in these terms as well. Okay, there are some applications of actual causality. And this has to do with things I have been doing. So we have applied actual causality to explanations for query answers from databases. You have a database, you can be a huge database, and you suddenly pose a query and you see a result. The query is true or false, or you retain a particular value as an answer. Yeah? And then you want to say why I'm getting this value, why is this query being true if it is a Boolean query. Yeah? So in this case, the explanations are database tuples. I mean, in the tables you have tuples, and then the tuples are going to become the explanations for the query answer. And we would like also to quantify how much they contribute to the query answer, when they do. Yeah? Or they could be also attribute values in tuples, not only the full tuple, but particular values. For example, if I have a tuple considering the socioeconomic situation of an applicant to a loan, it could be the salary, for example. Yeah. So the tuples get responsibility scores, as before, quantifying how much they contribute. Yeah? And we have established some connection with model-based diagnosis. And actually, we have profited from those connections. It's not just a theoretical game that we say, oh, this is nice, this corresponds to this, and this is a nice connection. When you establish those connections, you may try to gain something from the connection, right? Because you know something about the other area, for example, model-based diagnosis, and you want to apply ideas, results, algorithms to the new subject. So we have done, actually, in a paper that we published not long, we have also applied actual causality to explanations for outcomes from machine learning classification system, and that goes in the direction of explainable AI. We have been working both in data management and data science and artificial intelligence. What is important to realize here is that these methods, based on actual causality, actually, they don't need much the internals of the classifier. Basically, all you need in order to apply responsibility is basically to know the input-output relation of the model, because you make some changes, I mean, in the inputs, and then you see what changes, I mean, when an output comes out. So what I'm trying to say, they can be applied even with these black box models. That could be an advantage, because we may not know what is inside the classifier. It could be a mess completely. Yeah. Okay, so the classifier could be a black box, or could be treated as a black box system. Yeah, all we need is the input-output relation to do these computations. Yeah, we have, in terms of what I have been doing, we have devised declarative, that means logic-based methods to reason with and about counterfactuals, and compute responsibility scores. I'm going to make a case for the need for reasoning later on. We have, now you can say, what kind of logic? Well, we have used ancestor programming, that is a formal logic programming, that is a very nice paradigm that has many applications. I'm not going to talk about this today, but I have a full presentation about this. If someone is interested, I will be happy to present more about this. We are working on a precise and general connection with model-based diagnosis, and you saw the gist of the connections before, not the details, of course, but there are interesting connections there that can be exploited. That's the point. We have also experimentally compared responsibility scores with other local attribution scores, as they are called. They are local because we are trying to explain a particular input, not the whole system, a particular input, give an explanation for the particular input. And the attribution score, they're saying what is how relevant is this particular feature value for the outcome that we are observing. Yeah? There are also other scores like causal effect that comes from causality in observational studies. And today, most prominently, the most popular score in explainable AI is SHAP, that is based on the Shapley value of game theory. That, we have worked on SHAP as well. And also we have compared these, say, black box scores with other scores that are based or used with open models. For example, when you have connected logistic regressions, I mean, you have the model, yeah? Econometric model, I think there is a lot to do in that direction. Yeah? So in particular, we have used financial data for making these comparisons. And actually, these black box methods provide very nice explanations in comparison to those methods that rely heavily on the model, the logistic regression model or the econometric model. Which is a nice result, I think, experimental result. So we have established that the score computation behave better when applied with an open classifier. What you see, maybe we do have access to the classifier. We have the null internals. If we apply these score computations, I mean, with these open models, for example, with RESP or SHAP, in particular with SHAP, we have done this. We can prove that we can, in some cases, very general cases, not minor cases, important cases, we can actually compute things much faster. And that can be stated in very precise terms. When we have an open classifier, taking advantage of the structure of the model to do the computation, to help with the computation, not only the input-output relation, because that is going to blow up in terms of all the combinations you can consider. I don't know if I make the point. If you exploit the model, the internals of the model, you can compute things much faster than when you use only the input-output relation. Of course, this is mathematical work. I mean, basically, it's related to designing algorithms, investigating the complexity of the problem, and so on. There is a lot of research to do in all these fronts, and there are many open problems, many research directions that are worth investigating, and that's what we are trying to do. Okay, let me come back to the responsibility to explanations in machine learning, and I'm going to start with a very simple example, the one I used at the very beginning. So responsibility and explanation. So we have the classifier, we have the applicant that is applying for a loan, and then the answer is no. Yeah? So E is what I had before, a record of feature values, or a tuple if you want. For this one, we get a no as a label, as a result, and then we could have some counterfactual versions. For example, E prime changes the age of the applicant to 25. In this case, if we change this and we put this E prime as an input for the system, we get a yes. Yeah? Well, maybe that is indicating that the age of the applicant, the real age, is something that we should consider, right? Or the second entity, we are making two changes. I mean, we are changing the salary from 70K to 80K, and now this poor person is moving from Harlem to Brooklyn, and then we also get yes. The loan is approved. Yeah? This is what we can see, I mean, playing with the classifier and local changes. So for the gist, I mean, in this case, the value for age is a counterfactual cost with explanatory responsibility of 1. It's only one change. It doesn't need any contingent changes, additional changes. So we have a maximum responsibility. The value for income is an actual cost with responsibility, in this case, 1/2, because we need an additional change. It would be 1 over 1 plus 1. The additional change would be 1/2. So it is less strong as a cost for the outcome that we are observing. Yeah? This is the gist. Okay, so in more general terms, what do we have here? We have a responsibility for a particular entity and also for a particular feature, a feature F. We are concentrating on a particular feature. It could be age, for example. Yeah? This is F star. And we want to get a score for associated to this feature for this particular entity. And that's what is make this local. Yeah? So we want a score for the value of feature F star in this particular entity. And what we have is an explanation for label 1. It could be 1 or 0 or yes or no. It doesn't matter. We are starting with a label that we want to explain. In this case, I chose to use 1. And then what we are seeing here is I make a first change from X to X prime there. I see on the right-hand side, what is in black is the classifier. I still get the label 1. Yeah? So I can play with this, and for example, that's what I observed in the second row here. I still get the 1 by changing X into X prime. And then let's leave X alone for a while, and let's try to change other values. So I'm changing X into X prime and Y into Y prime, and I do not observe any change. Still I have a 1. And now let's see if by making the original change again, I get something different. So now x is changed into x prime. I have these two changes, and now the label, as you see, is 0. I managed to switch the label. Yeah? So what do we have here? We have that x becomes a natural cause for obtaining a 1, and x prime and y prime are associated to a contingency set for this particular x that we change from x into x prime. Yeah? So this is the idea, and then this is what I just explained. So x is a counterfactual explanation for the label equal to 1 if by making the change x into x prime for some x prime in the domain of the feature, let's say from 18 to 25, I switch the label, then in that case I say that x, the original value, is a counterfactual explanation. That's what we had before. I'm trying to make this more general. And now x is an actual explanation, causal explanation for the label 1. If there are values for other variables, y here, and new values for those variables in y, I mean this is the x prime and y prime, and I'm making also a change of x into x prime. And then in this case I get, first of all, that by making only the change of the contingency set, making only those changes, I still have the same label, I haven't changed anything. But if in addition to this I make the change from x to x prime, I do switch the label. So that is the definition of an actual explanation in this case. Yeah? And then how do we compute the responsibility? Well, we basically play with the game considering the minimum size contingency sets for the original x. So maybe I made too many changes here. Maybe x prime was good enough, or y prime was good enough to accompany the change of x. So for a minimum size contingency set y, the responsibility of the value for feature f star in this entity E is equal to 1 over 1 plus the cardinality of y. And y has to be a minimum size contingency set. Yeah, it's the minimum number of changes that you have to make in addition to the change of the feature at hand that we are investigating. Make sense? No? Okay, it works nicely, but it works nicely actually when you have binary classifier, because you have basically play with zeros and ones. So what happens when we don't have binary features? Well, thing has to be extended a bit. We haven't provided a better model, because actually it could be the case that if I change x into x prime, I do get a 1. But if I change x into any other possible value in its domain, I do not change the label. So how strong is the explanation, x, for the 1? Maybe not so strong, because it is overweighted by many other situations where the changes do not change the label. So we have to be more refined. So towards a more general definition, for binary features, the previous definition works fine. Otherwise, as I just said, there may be many values for a feature that do not change the label, and the original value is not a great explanation. Yeah? Only x to x prime works fine, but all the other possible values for x do not change the label. So the first attempt is to consider all possible values for a fixed feature, in this case f star, without contingent changes, yeah, of other values. I'm just fixing one feature and considering all the possible changes of values for this feature f star. Yeah? So in this case, it's better to consider the average label, because as I said, there might be many cases where you still get the old label, and now only for one case we get the new label. So we average label obtained this way, and the responsibility in this case is expressed as an expected value, yeah? An average. An expected value is an average, right? We did this in a paper a couple of years ago. So basically what I have here is what we call counter score. Basically I have the label 1, and I compute the difference between the original label and the expected value of the labels when I only change values for f star. So I can see all the possible changes from x to something else, leaving everything fixed for the other feature values. I will get ones, zeros, ones, zeros, ones, zeros, and then I compute the expected value, and I compute the difference with the original label. Yeah? So that is better than, because we have now possibly non-binary features. Yeah? So this score is very simple. It's just consider only one feature. It's easy to compute, it's worth trying, and actually we did experimental work with this and actually give quite reasonable results. Very simple, very, very modest, approach. But it's still, as a first approach, it can be tried out. Of course, when we compute expected value, we need a probability distribution on the entity population or some approximation or estimation of the probability of the underlying population. Yeah, we are considering all the possible entities, right? Some of them may be more likely than others, so that has to be brought into the expected value, of course. Okay, but what is the problem? This counter doesn't consider other feature values, that's fine, but it could be the case that making one change alone, no matter which change you make, with this fixed feature doesn't change the label at all, never. So now we want to bring into the picture also the possibly contingent changes in addition to this. So this is an extension of the counter score, basically. So now the general definition would be as follows. Motivated by this, I repeat, I believe in the power of sermon, of repeating things. That is the way you make the message go through, okay? Changing one variable, no contingencies, may not switch the label, so no explanations are obtained. So better consider both contingencies and average labels. Now putting everything together, basically. Yeah? So we have an entity under classification. This may look a bit complicated, but it's not very complicated. We have a label 1. I have a feature, F star, that we want for which we want to do play this game to explain the relevance of the value associated to F star for the classification. So we start by basically changing values in contingency sets. I'm not going to change the feature value for F star. I'm just going to start playing with the other values. Yeah? So this is going to be a local responsibility score. We fix a contingent assignment, that is gamma or W. W are the new values for features outside F star, the one that we are considering. Yeah? So the local responsibility score is basically everything we had before, but in this case we are going to take two things into consideration. We are going to consider here in the denominator the size of this contingency, the set of contingency features that we are going to make changes upon. Right? And here I have the same as before. Basically, I'm going to see what I get for the label when you basically, okay, E prime here is whatever I get when I change all the values in gamma, this set of features, into according to W bar. So I'm making changes, local changes for features that belong to this set gamma. I will get a label. Basically, in this case, I'm expecting the label not to change because I am trying to make a change in the feature, in the value of feature F star. So, but I only have this label for this entity with these changes made, for the contingent features, yeah, minus the expected value where I change two things. I not only change this, but I also change the feature at hand from whatever I had at the beginning into V. So I'm making all the difference between the label I obtain for this particular change, that's a fixed change with the W for the values of the contingent features, minus the expected value that I get when I change, make changes considering all the possible values for the feature at hand. Again, it's the same as a generalization of what I had before. The only difference is that I'm fixing a set of contingent set and I'm fixing their values with W bar, and then I play the same game as before, and I'm bringing into the picture the size of the contingency set or the assignment that I'm using. So this depends on what? It will depend on W, and will depend on the size of the contingency set gamma. Yeah. So basically, in order to get the final score, all I have to do is, I'm going to skip this basically, all I have to do is maximize, this responsibility score, considering all the possible gammas and W's, but considering minimum cardinality set of contingency values. I consider minimum cardinality set of contingency values, and then I take the maximum of all those local responsibility score, and now I make, with this maximization, W and gamma disappear basically, and I get a score for the change from the original value, whatever value we had for F star, into something different. Yeah? So this is will be the general definition of responsibility score. We have we use this score in this paper I just mentioned. We compare it with different other scores that are in the literature. Actually, it works pretty nice. But there is one point I would like to make here. This is not necessarily easy to compute. We are considering many combinations. Actually, we can prove that for some classifier, actually Boolean classifier, this can be intractable in very precise terms. I mean, it can be computationally hard. Yeah? Actually, for those who know about this complexity issue, it can be sharply hard. That is a sign of hardness, of intractable computation. Okay, some remarks. We are usually interested in max responsibility feature values. Those are the most informative in some sense. Yeah? Maximum responsibility. Yeah? Age is very important in this case. Yeah? So they are associated to minimum cardinality contingency sets. Yeah? We know that that's what because I maximize over cardinalities of contingency sets. Their computation, as I just said, is in some cases that we have characterized, provably intractable. We can prove a theorem, okay? Responsibility, as I said before, does not require the internals of a classifier. So here there is room for interesting research. Can we compute this score faster when we have access to the internals of the model? To the best of my knowledge, nobody has addressed that problem. That's a very interesting research in computational complexity and involving mathematical developments. It's very interesting. We have done this with SHAP, so we know it can be tricky, but it is possible. Yeah? Also relevant, we want to do something with a high responsibility explanation. So I get an explanation, what I can do with that? So I'm going to a higher level of discussion here at this point. We want to do something with that, right? For example, some counterfactual may not make sense or be useful in applications. We need more than just an explanation. We want to do something about that, right? Can we do something for this guy who is applying for the loan and has been rejected? We cannot say, well, 18 is too young. You have to wait 7 years until you become 25 to get the loan. So sorry, give me a break. That's not what I need, okay? So not all the time the most informative causes are those that are useful in practice. So we have to cover the whole scenario. Yeah? Okay, in the example, changing the age, waiting 7 years, for 7 years may not be feasible. Yeah? And actually, but maybe changing the job and the neighborhood where this guy lives, is feasible, something that can be done. We may want an actionable explanation. That is a term that appears everywhere in the literature these days. Actionable explanation, or also what is called a resource. I want the explanation to be useful, leading to an action, something that can be changed in order to get a different outcome from the classifier. I'm not going to say more about that, but then you may start seeing that there is a need for reasoning, because we have to specify what is an actionable explanation, what is not. Maybe we want to reason with them, which of them is better, etc. And there's a lot of room for interesting thing here. So the need for reasoning, that I wanted to make a case for the need for reasoning. What can we do with attribution scores and counterfactual explanation? That is the general question. Apart from the obvious that getting the age is a strong cost. We can reason with or about them, about these counterfactual explanations, right? We want to analyze them. We want to select some of them that are better than others in some sense that has to be specified, hopefully logically. Yeah? We might want to aggregate them to have a more general picture of the whole classifier. So maybe we start seeing many explanations showing that because of the age, people don't get a loan. Maybe we might want to change our policies, right? Well, maybe 18 is too harsh. Maybe why not compromise, say, maybe 20, I don't know. Something can be learned, at a higher level about the whole classification system by playing, analyzing, aggregating an explanation like this. And that is also an area in which much has to be done in terms of research. Yeah? So, and this analysis can be done in interaction with both with the attribution score algorithm and the classifier, because it's a game that you are playing, right? To see different outcomes, yeah? For further exploration, yeah? And also for global understanding of the classifier or the application domain as well. It also tells us about, assuming that the classifier is basically fine, it tells us a lot about the application domain, about the people who are applying for loans, etc., etc. The age of the population. So there are many things that can be obtained from this. So we need tools for conveying or imposing domain knowledge, or what I call domain semantics, the meaning, capture the meaning of the application domain. Yeah? For example, I would like to specify that an age never decreases. What's the point of start playing? You have a 18 as a feature value of age, of playing with 18, moving 18 to 16, for example. I mean, that doesn't make sense. I mean, age always increases. We can only wait, but not go back in time. Well, at least in the form of time that we use. Yeah? So only some counterfactuals may make sense, and some combination of feature value may not be allowed. For example, some combination that I don't want to play with counterfactually. For example, someone who I do not want to end up with a counterfactual or analyzing or bringing into the computation a counterfactual where the age is 6 and the person is at the same time married. I mean, I don't know. I don't think maybe there is a society or a country where that may happen, but that is usually not the case. Yeah. So these things can be specified, and they have to be brought into the counterfactual game and into the score computation. And there is a lot to do in that direction. I think a very important research direction. Also, it might be the case that some changes triggered other changes. I mean, if I change this, I am forced to change the other one. I mean, that has to be taken into account and not leave this other feature independent from the other. I mean, so this is also, how can you don't want to hardwire these things in a computation, in a score computation or definition. You want to use this knowledge as an input to the computation. That's what I'm trying to say. Yeah, it's very difficult to hardwire all the things for every possible application domain. Better have declarative knowledge about the domain that can be used in combination with the definition of the score and the computation. Yeah, that is my main message. I have been working in that direction. I have a couple of papers on that. Yeah? So we might want to impose preferences on counterfactuals, and I have worked a bit on this as well. Yeah? So we need tools for doing this kind of logical reasoning. I'm almost very close to the end. We need tools for posing and answering queries about explanation, because we have a system that reasons, but you also want to pose queries on top of the whole combination of the reasoning system. Does this happen or not? Yeah. If this is a counterfactual, well, I'm going to give a few examples. So are there explanations with this particular property, for example, where I have now a different age? I can pose a query to this reasoning system and I get an answer. Yeah? Or a counterfactual where this two explanations that differ by the value of this particular feature would be interesting for exploration to see if I can detect those cases. Yeah? I would like to also specify, apply reasoning to the specification. When I talk about reasoning, I'm also talking about logical representation of things, about declarative specification. So I would like to specify high score actionable explanations, right? And possibly computation of those only. I'm not interested in other counterfactual, only on the actionable ones that have the highest possible score. Or others with a different preferred property, not only actionability. Yeah? We would like to have some sort of on-the-fly interaction with different machine learning models to explore if other models behave differently, and this on the same logical basis, interacting with different classifiers, and a score algorithm for score computation. Do I get the same score with this different machine learning system than with this other that I was using? That is something that can be done, I mean, in this kind of combination of logical and algorithmic approach. Or can I get a different values? Instead of using this RESP score, I use SHAP, for example. All this could be brought into the same picture related to reasoning. Yeah? Also, we would like to possibly impose conditions on feature values. What if I leave some feature values fixed? I want to have this fixed. What do I get? I mean, something that I could be easily specify on the fly without having to change the algorithm for computing scores. Do I get some high score feature with this similar entity? I could specify a similarity notion. Say these two features are similar in this condition. Do I get the same labels and scores and so on? They could be compared. Is there a high score counterfactual version of the entity that changes this specific feature? I'm interested in examining this one, and I still get a very high score. Or never changes this one. I don't want to change the age, for example. It's a query. Is there something? It's a query that, like the queries that you pose to a database system. I should be able to answer them. Well, with this logic-based approach that I hinted to, it is possible to do this. Okay, I want to finish with some observations about where do we take it from here, beyond explanations. Explainability in AI is related to other dimensions of ethical AI. Yeah? I put everything into one single bag so far. But especially in combination with reasoning, I think this is particularly related to other considerations, dimensions of ethical AI. In particular, there are some recent papers that relate causality and explanation with fairness, fairness of system. I don't want the system to show any bias. I mean, so that person has, I don't know, a particular race. I mean, he's going to never get the loan or the other way around. Now, we want AI and machine learning systems to be fair. Of course, we have to give a precise definition, or there are precise definitions. Actually, maybe too many definitions in the literature in this moment, but this is the idea. But reasoning and query answering can help us specify and detect unfair situations or behaviors. That's important. So you can, by posing queries, you can detect situations where you may be involved in some sort of unfair, decision making. Yeah. Actually, I have colleagues of mine with whom I have collaborated in the recent past who have been actually concentrating on what kind of queries are important to detect fairness issues. Okay, for example, here we have this very simple example that shows the gist. I have a decision tree here, and I could specify what is a protected feature in a very precise sense, but I can specify. For example, I want to protect the feature race. What is going on here? I have basically two entities that have followed the same, have the same history up to a certain point. Yeah? The 1 and 2, they are following this path along the decision tree, and suddenly they reach feature race, at which point they start diverging. And actually diverging, and then they get different labels. Maybe that is a situation that is not particularly desirable, and you might want to detect these situations, right? Yeah? So the path of the decision trees for the two entities diverge at some point. At that particular point, at the point of the protected feature that you specify as such, we want to pay special attention to this particular feature, getting different labels so that you can detect those things. You can actually reasoning about these possible cases, pose queries about entities that exhibit this kind of behavior, and you will be in position to detect problems like this. Yeah? So basically, by keeping track of counterfactual histories and compare them, that is something that can be easily done with this logic-based approach. I hinted to it, but I didn't present today. So in the last slide, I have only, I think we are going to share the slides. These are papers I have published in the last few years that are related to what I discussed today. I didn't want to go into too many technical details, but I wanted to give the overall picture. Something that I didn't mention too much is that we have done work in the AAAI paper 2001 with some colleagues in Chile and in Lille about the tractability of SHAP computation when we have open classifiers that are particular kinds of binary decision diagrams that include important things like decision trees and other well-known classifiers. So we have been able to show that SHAP can be computed in polynomial time as opposed to the, in principle, exponential computation that is involved in the definition of the score. This research has not been done for RESP, and I think that is very important to do that as well. Responsibility is something has been around. I mean, causality, actual causality, I really want causality to play an important role in this discussion. And actually, it is playing a very important role in whatever has related to fairness in AI in these days. So it is worth investigating what causality, actual causality, can bring to the table, as opposed to maybe inventing ad hoc scores for explaining feature values. So there are many things to investigate, and I will be happy to discuss them offline and to consider possible collaboration with other people. Okay, that's what I wanted to tell you. Thanks a lot for the
Thanks a lot, Leopoldo, for the great masterclass, really. You show your passion, your great experience on these topics. No, thanks a lot. We have still 10 minutes. If there are some questions, maybe you can write in the chat. You can follow up maybe offline directly with Leopoldo. But if you have some question, we can share now. I don't see the audience there in Montreal, so maybe there are questions in your audience.
Yes. René Garcia, so I have a question for Leopoldo. So you concentrated on the age variable, which is a numerical variable. But the thing is, if I had taken plumber, okay, so I find that plumber is one specific occupation. And I was wondering if you enlarge this specific occupation to a larger class of occupations will be easier in terms of explanation, because in a sense also that will be also the case for salary, because occupation and salary are related. So I mean, in a sense, if you make salary very precise, then so you could make classes of it would be between 50 and 100 or 100 and 150. So I was wondering the definition of the features, how much it helps in finding explanations.
Well, your question actually touches my heart. I mean, it is one of the problems I am starting to investigate with a student of mine. I think it's a very important problem because features, they usually have something like a hierarchical structure. Yeah. So actually, what is very important to do, and that goes in the direction of your question, is to have categories of features that are related to something relevant. For example, socioeconomic status or situation of a particular applicant, where you may have maybe the occupation, I don't know, the salary, neighborhood, and other categories that are related to other issues like age, more personal features, right? So I think there is a lot to do in the direction of actually defining scores for categories of features. And if you have categories of features, actually, you may have not only categories, but you may have also complete dimensions. I mean, the dimension, socioeconomic situation. At the very low level, you have the salary. At the higher level, you have, let's say, a kind of job that somehow implies, different salaries that are high or low. Yeah? So you have categories that are hierarchically organized according to a dimension. And you might want to navigate those dimensions going from one category, for example, to higher level ones. And that is exactly what you are saying. And I think that is something that has to be explored. There is some research in that direction, but I think the big picture has not been addressed so far. We need a proper definition of values for sets of features, for example. Yeah, that would be still very narrow. I really want to bring into the picture a multidimensional structure of features and take advantage of that. Those multidimensional structures have been used in data science, data management for a long time. The most obvious incarnation is data warehouses, right? Multidimensional databases, where you can navigate different hierarchies, right? And you can actually use computations or values at the lower levels to compute values at the higher level, yeah, by aggregation. So I think that is a fascinating area of research. When can we get something like a score for a higher level category by aggregating scores at the lower level, things like that. I mean, can we profit from all the techniques from data management, for example, to aggregate and manage these scores in order to obtain meaningful results, as we do in business intelligence with multidimensional databases? I think there is little done in that direction, and I think it's a crucial direction that is something that I really, well, we are starting to scratch the surface, I mean, in terms of the research that we can do in that area. Yeah, you're completely right.
Are there other questions on your board, Margarita?
Yeah, I'm on board. So if there are no other questions, maybe we can end this masterclass.
René has a...
I have another question.
Please do. Yes.
So you mentioned that it's possible to consider only the input and the output. So if I place myself in a deep learning context with a multi-layer neural network, so in principle, then I can take the inputs, I mean the lower level of the network, and then consider the outputs, okay? Now, I could get, if I call these input features, I can get one feature and then associate it with the result that I obtain at the output, without considering the number of layers that there is in the middle and all that. I mean, is there are there fruitful results in this area, or?
Well, I mentioned before that we have been working with SHAP. What we did in that AAAI paper was to show that for certain classes of binary circuits, we can compute the SHAP score that is related to the shapely value in game theory in polynomial time, something that could not be done if you just use the input-output relation. And, well, you may say, well, what's the point? I mean, maybe you have a very simple class of classifiers for which you can do that. Actually, that is not the case. The class of classifier for which we have obtained these results can be applied to, for example, binary encodings of neural networks. Yeah? So, basically, we can reuse those results as are for general binary, well, not completely general, but a large class of binary classifiers, I mean, to the specific case of neural networks by doing this compilation of the neural network into a binary diagram.
Then you will use a path, no? Like between the input and the output?
No, it's not. Actually, no, basically you have to do is to bring the structure of the circuit into the score computation to make it faster. No, it's not that easy as following a path. I hope it would. But what I'm trying to say, and actually I have a student who is working exactly on that, and he's going to visit us next month or so, and he's doing exactly that. He's compiling neural networks into binary classifiers that fall in this class for which we have obtained tractability for SHAP score, and we are exploring. Of course, there is interesting theoretical research, but it's also interesting to see how much time it takes to explain or find score for a neural network treated as a black box in comparison to this compilation and doing the tractable computation game that we know it can be done. Yeah, I think that is basically you have to take advantage of the structure of the whole classifier to bring that structure into the score definition and computation. Yeah, but it can be done. I think there are still many interesting things to do in that direction. But we are working on that.
Thanks a lot. Margarita?
Yes, and so thanks a lot for this masterclass. I propose maybe to close now. It is 4:30, and then those who have a question can follow up with Leopoldo. Thanks, Leopoldo. Thanks, René, for making this possible, and also Catherine, Madeleine, for all the organization of this masterclass. And thanks to all the participants.
Thanks to all of you for your participation. And here you have my email in case you want to ask more or interact or explore research directions. I would really love to do research with other people. Okay, thanks a lot.